Hello, friends, and welcome to another lecture on chemical engineering thermodynamics. This is an interesting problem. The problem is on your screen. This problem is from grade 21 and it's problem number 38. The combustion of carbon monoxide is carried out in a closed, rigid, and insulated vessel. 1 mole of carbon monoxide, zero point 0.5 mole of oxygen, and 2 mole of nitrogen are taken initially at 1 bar and 298 Kelvin, and the combustion is carried out to completion. The standard molar internal energy change of reaction, that is delta U0R, for the combustion of carbon monoxide at 298 Kelvin is minus 282 kilojoule per mole. At constant pressure, the molar heat capacities of N2 and CO2 are 33.314 and 58.314 joule per mole Kelvin. Assume that the heat capacities to be independent and the gases are ideal. Take R is equal to 8.314 joule per mole Kelvin. The final pressure at the completion of the reaction is dash bar, round off to 1 decimal place. Now remember one thing, the statement of these kind of problems itself are very long, and as you read them it makes the challenge to solve it a bit daunting. But remember one thing, you always have to think very methodically while solving a problem. And a methodical approach, the way I am showing it, to solve one problem, remember, can be applied to solving hundreds of such problems. And the method remains the same. You do not have to improvise and invent new techniques each time to solve a fresh problem. So look at how I solve it. First, what is it? We have a closed system. So the reaction happens in the closed system. No mass goes in and no mass goes out. Now the first law for open systems is here on your screen. Now if we apply this, we will get du by dt is equal to, the first term is 0, that is because no flow is going in and out. The second term is 0 because no heat is going in and out. The third term is 0 because no work is being done, shaft work is being done on the system, and the volume of the system does not change. I define this black circle in which I have carbon monoxide, oxygen, which finally gives me carbon dioxide as my system. Its volume does not change. So what we have is du by dt is equal to 0, or this means du is equal to 0, or this means that change in internal energy of the system is 0. Having known this, what is the change in internal energy? The change in internal energy is nothing but the final internal energy minus the initial internal energy of the system, and this should be equal to 0. That is all. And if a reaction is involved, you have to just write the change in final internal energy minus the change in internal energy initial plus the change in internal energy due to reaction. Now this happens at 298, so we will, the standard stated as 298, so we put a 0 here and we are done. Now what is the final internal energy? The final internal energy is nothing but 1 mole of carbon dioxide into the CV of carbon dioxide, that is 58.314, into the temperature at which the system finally reaches minus the base temperature for the heat of reaction, that is 298 Kelvin, plus 2 moles of nitrogen into 33.314 into its final temperature minus the base temperature for the reaction. Now, initially, we have 1 mole of carbon dioxide into its CV is something which I do not know, into its temperature, which was the initial temperature, minus 298, plus 0.5 into CV of oxygen into its initial temperature minus 298, which is the temperature of the standard state of reaction, plus 2 into 33.314 into T initial minus 298. This will be written for the initial moles of nitrogen that we have, plus delta U 298 is equal to 0. Now remember, as given in the problem, Ti is equal to 298. Therefore, the these terms automatically get cancelled off, because when we put 298 in it, these terms automatically cancel off. And we are only left with 1 plus 58.314 plus 2 into 33.314. So 2 into 33.314 is equal to 66.628. 66.628. I have taken these terms as common, into T minus 298 is equal to minus delta 0 to reaction. Not 298, so reaction. It was delta 0 reaction. Now, so we finally solve this out, and what we have is 58.314 plus 66.628, that's 124.942. 124.942 into T minus 298 is equal to, the value that we are given is for delta UR is minus 282 kilojoule per kmol. So that's going to be plus 282 into 1000 joule per mole of a reaction. Remember, it's for a mole of a reaction. Now, a mole of a reaction is when 1 mole of a reaction takes place, we have 1 mole of carbon monoxide giving you 1 mole of carbon dioxide. So that's fine. So the answer here now is T minus 298 is equal to 282,000 divided by 124.942. and that is 282,000 divided by 124.942. This is equal to 2257. That's equal to 2257. So that is it. That is what we have got. So he's asking you the final pressure. So that's the increase in temperature. So if you want the final temperature, this is going to be 2257. Should I be considering the decimals? No, not required, because they are insignificant. Plus 298. This is going to be equal to 2257 plus 298. That's going to be 2555. 2555 kelvins. Now we need to find out what is the final pressure. That's right. So the final number of moles is 2 moles of nitrogen and 1 mole of CO2. This is what we have. So we have 3 moles. The final temperature is known. It is 2555 Kelvin. Now the last bit that is required is what is the volume? The volume can be found out from the initial conditions, which is 1 mole of carbon monoxide plus 0.5 moles of oxygen plus 2 moles of nitrogen into 298, which was the temperature, divided by 8 point into R into 8.314 divided by the pressure. Now the pressure was 1 bar. So 1 bar is 100 kilopascals. So this will lead us to we need not do the calculations. We can always replace it. So let's drop the calculations and let's leave it at 1 bar itself. 1 bar itself. Now the final pressure is going to be nothing but equal to this was the final moles were 3 moles into R into 2555 divided by V. That is 2 plus 1 3, 3.5 into 298 into R divided by 1 bar. So cancelling off the like terms and solving it off, we get the answer in terms of bars. So let's solve it out. 3 into 255 divided by 3.5 into 298. Now that would make it 3 into 2555, that is equal to so much, divided by, starting the bracket, 3.5 into 298, end the bracket, we got 7.34, which is this is equal to 7.34 bar. So the final pressure is nothing but 7.34 bars. It was such a simple solution, it was such a simple concept, and this is the most direct and straightforward way of understanding it. Remember one thing, now this can be applied to any such closed system problems where reaction is occurring. In any closed system where a reaction is occurring, this fundamental can be applied. So that will be all, guys. Hope this explanation did fire the zeal in you to attempt all the problems in chemical engineering thermodynamics and ace it in the exams. Do write whatever you feel in your comments. Of course, the comments should be positive, and if you have any doubts, do write them in your comments. And if you have any novel problem, send it over. I will try to see and make a video out of it. Okay, guys, have a great time. Goodbye.